You know, when people ask me about the atom, they often expect a simple answer. They want me to tell them what it looks like, how it works, as if I could hold one up to the light and show them its inner machinery like a watchmaker displaying the gears of a clock. But I must disappoint them, or perhaps intrigue them, by saying that the atom is not like a clock at all. The atom is a mystery, and it remains a mystery even now that we understand so much about it. This is not a failure of physics, you see, but rather a profound insight into the nature of reality itself. Let me begin with something personal. When I was a young man in Copenhagen, studying physics at the turn of the century, the atom was already an old idea. The ancient Greeks, Democritus and Leucippus, had imagined indivisible particles they called atoms, but this was philosophy, not science. By the time I entered the field, we had real evidence for atoms. We knew matter was made of discrete units. We had Dalton's work in chemistry, we had Avogadro's insights, and we had the beautiful experiments of Jean Perrin that showed Brownian motion could only be explained if tiny particles were constantly bombarding larger ones. The atom was real. But what was it? That was the question that consumed me. John Dalton had imagined atoms as solid spheres, like billiard balls. J. Thomson, after discovering the electron, proposed what people jokingly called the plum pudding model, where electrons were embedded in a positive sphere like raisins in a dessert. Then came Ernest Rutherford's extraordinary experiment, the one where he fired alpha particles at gold foil and found that most passed straight through, but some bounced back as if they had hit something incredibly dense and small. Rutherford himself said it was as if you fired a cannon shell at tissue paper and it came back and hit you. From this, he concluded the atom had a tiny, dense nucleus with electrons somehow orbiting around it. I remember when I first learned of Rutherford's nuclear model. I was immediately fascinated, but also deeply troubled. You see, there was a fundamental problem with this picture, a problem that anyone trained in classical physics would recognize immediately. If electrons were orbiting the nucleus like planets around the Sun, they would be constantly accelerating, constantly changing direction as they moved in their circular paths. And according to Maxwell's equations, any accelerating charged particle must radiate electromagnetic energy. This means the electrons should be constantly losing energy, spiraling inward, and crashing into the nucleus in a fraction of a second. Every atom in the universe should collapse instantly. But atoms are stable. The chair you sit on, the air you breathe, the very cells of your body, all are made of atoms that have existed for billions of years without collapsing. This was the crisis I faced when I went to work with Rutherford in Manchester in 1912. The nuclear atom was real, we had experimental evidence for it, but classical physics said it was impossible. Something had to give. Either the experiments were wrong, or our entire understanding of physics was incomplete. I chose to believe the experiments, and to accept that classical physics, as beautiful and successful as it had been, could not describe the world at atomic scales. This required a kind of courage, or perhaps audacity, because I was essentially saying that the laws of physics that worked so magnificently for everything from falling apples to orbiting planets simply did not apply inside the atom. But I was not working in a vacuum, you must understand. Max Planck had already introduced the quantum of action in 1900, showing that energy could only be absorbed or emitted in discrete packets when dealing with blackbody radiation. Einstein had used this quantum idea to explain the photoelectric effect in 1905, suggesting that light itself came in particles, or quanta, which we now call photons. The quantum was already in the air, so to speak. What I did was to apply the quantum idea directly to the structure of the atom. I proposed that electrons could not orbit at just any distance from the nucleus, but only in certain allowed orbits, certain stationary states. In these special orbits, the electron would not radiate energy, even though it was accelerating. This was a radical departure from classical physics. I was essentially saying that the laws of electromagnetism, which had been so carefully worked out by Maxwell and verified by countless experiments, simply did not operate in the usual way inside the atom. The electron in one of these stationary states would remain there indefinitely, stable, not radiating. But if electrons could only exist in these discrete orbits, how did they move from one orbit to another? This is where the mystery deepens, you see. I propose that when an electron jumps from a higher energy orbit to a lower one, it emits a photon, a quantum of light, whose energy is exactly equal to the difference between the two energy levels. The formula is simple and beautiful. The energy of the photon equals Planck's constant multiplied by the frequency of the light. This explains something that had puzzled spectroscopists for decades. When you heat an element, or pass electricity through it, it emits light at very specific wavelengths, creating a unique pattern of spectral lines. Each element has its own signature. Hydrogen, the simplest atom, has a particularly simple spectrum, and there were empirical formulas, like the one discovered by Johann Balmer, that could predict the wavelengths of these lines. But no one understood why. My model explained it immediately. Each spectral line corresponds to an electron jumping from one allowed orbit to another. The discrete nature of the orbits means the emitted light comes in discrete frequencies. When I calculated the energy levels for hydrogen and predicted the wavelengths of its spectral lines, they matched the experimental values with extraordinary precision. This was one of the great triumphs of early quantum theory, and it convinced many physicists that I was on the right track. But here is where the mystery truly begins, the mystery I want you to appreciate. What happens when an electron jumps from one orbit to another? In classical physics, if something moves from point A to point B, it must pass through all the points in between. But in the atom, the electron does not pass through the space between orbits. It simply ceases to be in one orbit and appears in another. This is what we call a quantum jump, and it is instantaneous and discontinuous. There is no trajectory, no path that the electron follows. It is as if the electron vanishes from one place and materializes in another without traveling through the intervening space. This troubled many of my colleagues, and I confess it troubled me as well. How can something move without moving through space? What is happening during this transition? The honest answer is that we cannot say. We cannot visualize it. We cannot create a picture in our minds that corresponds to what is happening because the quantum jump is fundamentally different from any process we experience in the macroscopic world. This is what I mean when I say the atom is a mystery. We can calculate what happens, we can predict the outcomes with incredible accuracy, but we cannot form a coherent, visualizable picture of the process itself. As quantum mechanics developed through the 1920s, this mystery only deepened. Werner Heisenberg, one of my most brilliant students, developed matrix mechanics, a completely new mathematical framework that could calculate atomic properties without any reference to electron orbits at all. Around the same time, Erwin Schrödinger developed wave mechanics, treating the electron as a wave rather than a particle. These two approaches seemed completely different, but they turned out to be mathematically equivalent, giving the same predictions for any experiment. Schrödinger's wave function was particularly fascinating and troubling. In his formulation, the electron is described by a wave that spreads out through space. The wave does not tell you where the electron is, but rather gives you the probability of finding it at any particular location if you perform a measurement. Before you measure, the electron does not have a definite position. It exists in a superposition, a kind of limbo, where it is potentially in many places at once. Only when you make an observation does the wave function collapse, and the electron appears at a specific location. This is where I had many long and difficult discussions with Albert Einstein. Einstein was deeply uncomfortable with this probabilistic interpretation of quantum mechanics. He felt that physics should describe reality as it is, not merely predict the outcomes of measurements. He famously said that God does not play dice with the universe. I understood his concern, truly I did, but I could not agree with him. The question, "Where is the electron when we are not looking?" seemed to me to be a question without meaning. Physics, I argued, is not about describing some objective reality that exists independent of observation. Physics is about what we can measure, what we can predict, what we can know. If we cannot, even in principle, determine the position and momentum of an electron simultaneously with perfect precision, then it is meaningless to say that the electron has a definite position and momentum. This is the essence of Heisenberg's uncertainty principle, which is not merely a statement about measurement limitations, but a fundamental property of nature. Einstein would present me with thought experiments designed to show that quantum mechanics must be incomplete. The most famous of these was the EPR paradox, named after Einstein, Podolsky, and Rosen, who published it in 1935. They argued that quantum mechanics led to what Einstein called spooky action at a distance. If two particles are entangled, meaning their quantum states are correlated, then measuring one particle instantaneously affects the state of the other, no matter how far apart they are. Einstein thought this was absurd and must mean that quantum mechanics was missing some hidden variables, some deeper level of description that would restore determinism and locality. I argued that there were no hidden variables, that the correlations between entangled particles were real and fundamental, and that we must accept that nature at the quantum level simply does not behave according to our classical intuitions. I developed what came to be called the Copenhagen interpretation of quantum mechanics, which emphasizes complementarity and the role of measurement. Complementarity is the idea that different experimental arrangements reveal different aspects of quantum systems, aspects that cannot be observed simultaneously but are all necessary for a complete description. The wave-particle duality of light and matter is the most famous example. Light behaves like a wave in some experiments, and like a particle in others, but never both simultaneously in the same experiment. Both descriptions are true, both are necessary, and both are complementary. The role of measurement is equally crucial. In quantum mechanics, the act of measurement is not passive. It does not simply reveal a pre-existing property. Rather, measurement actively participates in creating the reality we observe. Before measurement, quantum systems exist in superpositions of possible states. Measurement forces the system to choose one of these possibilities. This is not because our measurements are clumsy or disturbing. It is because there is no fact of the matter about which state the system is in until the measurement occurs. I know this sounds strange, perhaps even mystical, but it is the only interpretation that is fully consistent with both the mathematical formalism of quantum mechanics and the experimental results. Over the decades since these ideas were developed, countless experiments have been performed, and quantum mechanics has been verified to extraordinary precision in every case. The predictions are never wrong. The formalism works perfectly. And yet, the mystery remains. Why is the atom a mystery? Because it refuses to fit into the conceptual frameworks we have inherited from our everyday experience and from classical physics. We want to think of electrons as little balls orbiting a nucleus, but they are not. We want them to have definite positions and velocities, but they do not. We want to visualize what is happening inside the atom. But we cannot, not in any way that is faithful to the actual behavior of quantum systems. And yet, this is not a failure. This is a discovery, perhaps the most important discovery in the history of physics. We have learned that nature at its most fundamental level is not deterministic, not visualizable, not describable in terms of ordinary language and common sense. We have learned that reality is far stranger, far more subtle, far more mysterious than we ever imagined. Let me give you an example that might help convey the strangeness. Consider the double-slit experiment, which Richard Feynman called the central mystery of quantum mechanics. You shine light or send electrons through two narrow slits onto a screen behind them. If you cover one slit, you get a simple pattern on the screen. If you cover the other slit, you get another simple pattern. But if you leave both slits open, you do not get the sum of the two patterns. Instead, you get an interference pattern, alternating bright and dark bands, exactly like what happens when water waves pass through two slits and interfere with each other. This shows that light and electrons behave like waves. But here is the mystery. Even if you send the electrons through one at a time, so that each electron goes through the apparatus alone with no other electrons present, the interference pattern still builds up gradually, one electron at a time. Each individual electron somehow goes through both slits simultaneously and interferes with itself, creating the wave pattern. But if you try to detect which slit the electron goes through, the interference pattern disappears. The very act of measuring which path the electron takes destroys the interference. It is as if the electron knows whether you are watching it and changes its behavior accordingly. This is not magic, and it is not consciousness affecting matter, despite what some popular writers have suggested. It is simply the nature of quantum systems. The electron does not have a definite path until you measure it. In the absence of measurement, it exists in a superposition of having gone through both slits. The measurement forces it to choose one path or the other, and this destroys the conditions necessary for interference. I spent much of my later life thinking about these questions, about the relationship between quantum mechanics and our understanding of reality, about the limits of what we can know and what we can visualize. I came to believe that we must give up the idea that we can form a picture of atomic processes that is both complete and consistent with ordinary language and intuition. We must accept that our descriptions will always involve complementary, mutually exclusive aspects that we can observe separately but never simultaneously. We must accept that measurement plays a fundamental, irreducible role in quantum mechanics, that the boundary between the quantum system and the measuring apparatus is crucial, and that this boundary cannot be eliminated or pushed back indefinitely. Some physicists, I know, are uncomfortable with this conclusion. They search for interpretations of quantum mechanics that restore some form of objective reality, that eliminate the special role of measurement, that bring back determinism through hidden variables or multiple universes. I respect these efforts, and some of them are mathematically sophisticated and internally consistent. But I have never found them necessary or even particularly helpful. Quantum mechanics, as we developed it in Copenhagen, works. It explains everything we observe. It makes predictions that are verified to incredible precision. And it does so without requiring us to posit unobservable entities or mechanisms. The mystery of the atom, then, is not that we do not understand it. We do understand it, perhaps better than we understand anything else in physics. The mystery is that understanding it requires us to abandon some of our most cherished assumptions about how nature works. It requires us to accept that the world is fundamentally quantum, that classical physics is only an approximation that works for large objects where quantum effects average out, and that at the smallest scales, nature is irreducibly probabilistic, complementary, and strange. This has profound implications, not just for physics, but for philosophy, for our understanding of knowledge itself, for how we think about reality and our relationship to it. I have often thought that the lesson of quantum mechanics is one of humility. We are part of nature, not separate observers standing outside it. When we measure a quantum system, we interact with it, and this interaction is part of the physical world. There is no view from nowhere, no God's-eye perspective from which we can see all aspects of reality simultaneously. We must choose what to measure, and this choice determines what aspects of reality we can observe. And yet, within these limitations, we have achieved something remarkable. We have developed a mathematical framework that allows us to predict the behavior of atoms, molecules, and all matter with extraordinary accuracy. We have built technologies based on quantum mechanics that have transformed our world: semiconductors, lasers, magnetic resonance imaging, the electronics that power modern computers and communications. All of this works because quantum mechanics is true, because we have correctly understood, within its proper domain, how nature behaves. But the atom remains a mystery in the sense that we cannot reduce it to familiar concepts, cannot visualize its inner workings in the way we can visualize gears and springs and orbits. The quantum world is different from the classical world, fundamentally and irreducibly different. And perhaps that is how it should be. Perhaps it would be disappointing, even suspicious, if the most fundamental level of reality were just like the everyday world we experience, only smaller. The fact that nature surprises us, challenges us, refuses to fit into our preconceptions, is a sign that we are actually learning something new, something genuinely profound. I think back to my time in Copenhagen, to the long discussions with Heisenberg and Pauli and the others who came through our institute, to the debates with Einstein, to the gradual, difficult process of understanding what quantum mechanics really meant. We did not have all the answers. We still do not have all the answers. But we learned how to ask the right questions, how to distinguish meaningful questions from meaningless ones, how to recognize when we were trying to force nature into inappropriate conceptual frameworks. The atom is a mystery, yes, but it is a mystery we have learned to live with, to work with, to use. We have learned that nature does not owe us visualizable models or deterministic explanations. We have learned that the universe is under no obligation to make sense according to our inherited notions of common sense. We have learned that reality is richer, more subtle, more wonderful than we ever imagined. And in learning this, we have not diminished the atom. We have not reduced it to something mundane and comprehensible. We have discovered that it is genuinely mysterious, genuinely strange, and that this strangeness is not a defect in our understanding but a fundamental feature of nature itself. This, to me, is not a disappointment but a source of wonder. The atom, that tiny, invisible constituent of all matter, that thing we can never see directly but only infer and calculate and measure, remains mysterious even as we understand it. And in that mystery lies the beauty of physics, the joy of discovery, the endless fascination of trying to comprehend the natural world. The atom has taught us humility, taught us the limits of visualization and classical thinking, and taught us that reality is far stranger and more marvelous than our everyday experience might suggest. And for that I am grateful. Claude is AI and can make mistakes. Please double-check responses.